শুভ নববর্ষ. Today we will discuss something about the states of a ammonia molecule, as it has been presented in the Feynman lectures third part. So we'll float obedient to the stream and discuss how Feynman tried to explain this. Ammonia, known as NH3. Ammonia, isn't it? Ammonia. Okay. We'll consider only one molecule of ammonia and how it is oriented. What is its structure? See, by experiments conducted, scattering experiments, it has been shown that it has a, most probably this is called a trigonal pyramidal structure. I don't remember the name although, but it looks like this. Hydrogen over here and hydrogen over here and hydrogen over another vertex of a triangle. Okay, this hydrogen, 3 hydrogen atoms form a base on which the nitrogen atom stands. So here, like this and like this. I think I am able to explain the three-dimensional configuration in this case. Okay, so I draw a line just through the centroid of the triangle and we'll imitate this figure but in a different manner. How? We'll consider two states. This is the first state, state A, and we'll consider another state, state B, and how it will be oriented. Just in the same manner, we'll take hydrogen over here and hydrogen over here also. Hydrogen. Okay, now the nitrogen has undergone a flip-flop. So how did it flip? Say the nitrogen is now at this position. We'll consider N here, nitrogen here, nitrogen over here, and here we link it. The same thing seen in different manner. This thing, if you see it from there, not from here, then this thing will come below, isn't it? The same thing has happened over here. If these two arrangements are considered as quantum mechanical states of the system, of the ammonia molecule system, then what will be the consequences? We have taken so easy, so simple state in order to describe this two base states. Base 2 states. Now we will describe any say the ammonia molecule is represented by wave function. Generally a particle is represented by a wave function, but a system, say the whole system, entire system, is written by the state. There are certain discrepancies or limitations in my presentation, but they will go all the way to make us all these errors corrigible. So this thing, let this state be state 1, okay, and this state be state 2. Then this thing can be written as C1 state 1 plus C2 state 2, isn't it? This is a hard and fast notation for it, simple as it will do. Now if you consider that if I am in this state, I will always be in this state, and if I am in this state, I will always be in this state. There will be no chance of leaking from this state to this state, as energy required for transition is not available. Then we can write the equations that lead to the Hamiltonian matrix, dc 1 dt is equals to, we don't consider leaks here, hence we can write h11 c1. This is actually a equation where you consider stationary state. So this is in one stationary state, this is in another stationary state. For the other, we write I h cut similar equation, dc2 dt will give us h22c2. Both of these equations can be solved, and the equations after being solved is given by c1 equals to some constant, say k1 times e to the power minus I h11 t by h cut. Similarly for c2, similar, we will have such exponential equation. These exponential equations carry with them I, and they will also be oscillatory. Okay, now if we consider that jumping from this state to this state is possible, jumping from here to here or here to here is possible, that say this be at greater energy, then it may reduce its energy by jumping to this state, and or it may increase its energy by jumping to this state. So we attribute to that a term called A, and A will give the Hamiltonian from 1 to 2. So this B equals to H21 by symmetry is equals to A, or minus A, you can write it. By writing it minus, we write along with the conventions. So the equation stands I h cut dc1 dt is equals to E naught. E naught is something which we have taken to be h11, and h11 is equal to h22 by symmetry. Then E naught c1. So they do not have different energies, yet they are flip-flopping from one state to other, isn't it? To and fro. So this thing plus hij, we have another hij h12, isn't it? into C2. This is H11. So this H12 can be written as what we have written here, minus A, isn't it? So minus A C2. Okay, and similarly IH cut D C2 dt is equals to E naught C2 E naught C2, yes, minus AC1. I have just inverted the sequence of terms. So now how do you solve it? So a ready-made way of solving this, first thing we will not consider these things. These things make the equation look clumsy, cumbersome, isn't it? So we write like this, ddt. We just sum them, C1 plus C2. This gives us C1 plus C2, C1 plus C2. So it comes as E naught minus A times C1 plus C2. Okay, now we are at the end of the board. This gives us C1 plus C2 equals to A times, see, we are solving a differential equation here. D C1 C2 equals to E naught minus A times C1 plus C2. So first thing that comes to mind is, what is that thing whose differential gives the same thing, and we know that it is e to the power x. So e to the power C1 plus C e to the power C1 plus C2 will be equals to e to the power something, isn't it, x, where x is the variable. Now here t is the variable, so it will be equals to something into e to the power t. So it comes likewise, a into e to the power minus I by h cut into e naught minus a into time. See, t comes over here, so it is an exponential in t. Similarly, if we subtract this from this, then we have C1 minus C2, which will give us B. This is another exponent into E times minus I by h cut here it is I by h cut into E naught plus A into T, because in subtracting we have just added E naught and A. Okay, we are done. Here we have C1 plus C2 and C1 minus C2, and this will give us C1 and C2 if we will solve the simultaneous equations. Okay, we'll start right from the beginning. This will give us C1, which is a function of t, and C2, This is also a function of t, and this will give us equals to a by 2 e to the power minus I by h cat e naught minus a into t. Okay, both terms will come. That means there will be something called b by 2, and this will carry along with it minus I by h cat e naught plus a at a time. If it is not legible here, we'll start from here, then it will be understable b by 2 into e to the power minus I by h cat into e naught plus a times time. That about C1. Similarly, we have an expression for C2. Now C2 will be the similar thing, but here in place of plus there will be minus, and we will have the solution of the equation. You have noticed that we have a first of all, see, after writing all this, if we let b equals 0, then what happens? If b equals 0, then b drops out from here and from here too, and we have this thing over here and here. That means if the amplitudes are equal for both the states of the system, it is equally probable for the system to be in state 1 and in state 2. Similarly, if a equals to 0, we'll have amplitudes, one of which is opposite to the other, but the total probability, the probability of the system to be in state 1 and state 2 will be equal for both a and b equals to 0. But since they have different what are these frequencies, isn't it? Frequencies of the probability waves. So the frequencies varies. For a equals to 0, then this term will appear. This is a higher frequency. For b equals to 0, this is lower frequency. This term will appear. The frequency gives the time evolution of the state. Now we can notice something here, that C1t plus C2t, if you sum them, then this thing and this thing cancels out, and this thing comes twice, and we have a e to the power minus I by h cat. This is a thing that repeats itself everywhere in quantum mechanics. See, E naught minus a into t. See, what we are seeing here is just like if say some of the two states gives sorry, these are not state coefficients of the state, is the coefficient of another state, say it may be, and it can be normalized here, and it will it just shows an exponential evolution. Exponential evolution is generally seen in stationary state with a given value of energy. So this may correspond to a given value of energy, and if it corresponds to an energy, then it will be E naught minus a here. E naught minus a. We'll later show that this corresponds to a new state in which the system can be analyzed. Similarly, if C1 minus C2t, we can see that this thing minus this thing, this will be 1, and this thing minus this thing will come out to be b to the power b e to the power E naught plus a, isn't it? Plus a plus. So then there will be another energy, and this will be given by E naught plus a. So there are so if flip-flop occurs, then we can estimate two separate states which are separated by an energy of 2a, isn't it? E naught plus a right over here, and E naught being here, and this is E naught minus a. So now E naught is a thing which you can take it arbitrarily almost. So basically this is minus a, and this is 0, and this is plus a. A transition of 2a occurs if there is a state jump. Okay. But we are not clear with the states. We will make it clear later on. Now, for the time being, we'll end our discussion by seeing, say, a molecule, the ammonia molecule is in state 1. Now, what is the probability, say the molecule is in state 1, no? Say the molecule is in state 1. So what is the probability of finding it in state 1? 1. And what is the probability of finding it in state 2? It is 0. Now we will see the time evolution of the system. After time t, what will be the probability of finding the system in state 2? So first of all, we will notice that we will use these theorems here, over here. C1t, this gives time evolution theorem. T is 0, then here t is 0, here t is 0, equals to a by a plus b by 2, isn't it? A plus b by 2. And the next thing comes is C2 over 0 equals to, here will be a by 2, here will be b by 2, and rest thing will be e to the power 0. Then this will be a minus b by 2. Now we know that C10 is 1, and C20, that is the amplitude of finding the state at time t equals to 0, that is the state 1 here in state 2, isn't it? So it is in state 1, so it is not in state 2, so this thing will be equals to 0 here. So solutions give A equals to B equals to 1. Solve it, then this will give A equals to B equals to 1. Okay, then we'll again substitute it into the main equations, and this will give e to the power minus I by h cut e naught t times into something which is very big here. We have e to the power I by h cut at. You can compute it mechanically by 2 plus e to the power minus I by h cut, the same thing, at. Okay, so if you go into this, we have e to the power I into something plus e to the power minus I into something. See, if we have e to the power I theta plus e to the power minus I theta, the first thing gives us sin theta cos theta plus I sin theta, isn't it? The second thing gives us cos theta minus I sin theta. The I sin theta cancels, then 2 cos theta. So here 2 cos theta will come over here and 2 will cancel out. The thing that will come will be only 1 cos theta, isn't it? And this is cos at by h cut. Similarly, c to t, this is the thing basically which you require, that what is the probability of finding the system, the ammonia molecule, in state 2 given that it was in state 1 at time 0. It will be equals to e to the power minus, by similar arguments, I by h cut e naught t times I sin at by h cut. You see a symmetry between the two equations? Yes, I see it. For C1 square gives you the probability of finding it in state 1, and this is given by magnitude of C1 square. So this thing will with its as it is an exponential with I, so this thing will when its amplitude is found out, it will be equal to 1, and this thing will square and it will become cos square at by h cut. Similarly, the p2t, the thing we require, will be equals to sine square. See, I and minus I will give you plus 1. I and minus I, why? Minus I is the complex conjugate y, isn't it? So this will give us sine square at by h cut. So what we see is they both of them oscillate with a certain similar frequency. So if you plot the probability distribution of state 1 and state 2, for example, we are first plotting state 1, so it is cos square at h cut as with time, and here is the probability pt with time. Then cos square, cos 0, we know that it is equals to 1, isn't it? So cos square is also 1, and cos 90 degree is equals to 0. So here, if time equals it can be calculated from here. It will be something multiplied by pi by 2 here. I think h cut pi by 2 by a. Okay, over certain distances it will vary, and cos square will look like this way, and this is over the same interval. Here it will have the maxima over here. Sorry, it will have the maxima over here. Maxima over here, and the minimum, and there will be another maximum over here. In this way it will continue, and the sine square will be just the it will be delayed by phase difference, isn't it? Of how much? Pi by 2, I think. Yeah. So this will be like this. Say helical, isn't it? Both of them meet each other helically. So this will be the lesson of today, and next day we'll talk about measure refers to similar to laser. It is microwave amplification by stimulated emission of radiation, and it can be put into practice by using the ammonia molecule for the energy that has been spent. The A or 2A, the energy difference between the two states 2A is of the order of the energy of a photon in the microwave spectrum. Okay, thank you.